This is lesson 5.1, and today we're going to be talking about intermolecular forces. Our goal today is to learn what an intermolecular force is and how different intermolecular forces work. So to start off, let's just define a few things. First of all, an intramolecular force is a force within or inside a molecule. And so intramolecular forces are different from intermolecular forces. Intramolecular forces are covalent bonds. You can see here pictured there are 4 water molecules, 4 H2O molecules, and the red here is going to represent oxygen, that gray is going to represent hydrogen, and within that molecule you have intramolecular forces, which are your covalent bonds. They're the forces that are holding together the molecule. Now, you also have things known as intermolecular forces. An intermolecular force is a force between different molecules. So there's a force of attraction between these different neighboring water molecules. Between this water molecule and this water molecule, there's a force of attraction. And that force of attraction we call an intermolecular force. So keep that in mind. Intermolecular forces are forces between different molecules, whereas intramolecular forces are forces within a single molecule. And to help you remember that an interstate is a highway that goes between different states. And so an intermolecular force is a force that is between different molecules. Also, please keep in mind that these are generally attractive forces. All of these intermolecular forces are attractive. They're not repulsive in nature. And the basis of all of these forces is really simple. It's just electrostatic attraction. That is, positive and negative attract. Opposite charges attract. And that is the basis of all of your intermolecular forces, as well as all of your intramolecular forces. And so let's just delve into it and talk about these different intermolecular forces. The first one is arguably not even an intermolecular force, and that are your ion-ion forces. Your ion-ion forces are forces within ionic compounds, and they're simply an attraction between positive and negative ions. Your anions and cations attract, which is a good way to start when we're talking about intermolecular forces, because the different things that affect your ion-ion forces are the same things that affect your intermolecular forces. So keep in mind that the larger your charges are, the stronger the attraction is. The larger the charge, the stronger the attraction between those different ions. Secondly, the closer those ions are, the stronger the attraction. So a shorter distance between your different ions is going to cause a stronger attraction between those ions. Now, let's try to make some sense of this by looking at these different melting points, which is real data here that we can kind of analyze these two different things. First of all, we have magnesium oxide and magnesium fluoride. Let's just focus on these two things. Magnesium oxide has a much higher melting point. And what does that mean? That means it's a lot harder to melt magnesium oxide. And when you melt magnesium oxide, you are effectively breaking those ion-ion forces. Not breaking all of them, but breaking them significantly. And so if we look at magnesium oxide and magnesium fluoride, we notice that magnesium oxide has a much stronger attraction between its ions, causing this higher melting point in magnesium oxide. Well, why does it have stronger attraction between ions? Because oxide is O2-, whereas fluoride is simply F-. You have a larger charge here for the oxide than for the fluoride, that 2- charge rather than the 1- charge, which means you have a stronger attraction between the ions within the ionic compound, making it held together by stronger forces, and so therefore it has a higher melting point. Now also notice that magnesium fluoride has a higher melting point than magnesium chloride. Magnesium fluoride melts at 1,263 degrees Celsius, whereas magnesium chloride is much easier to melt at 714 degrees Celsius. Why is that? They both are made out of magnesium, which is 2+, and a halide that has a 1- charge, right? Fluoride's 1- and chloride's 1-. So the charges of the ions is exactly the same. The only difference is chlorine is larger than fluorine. And so your chloride ions are going to be larger than fluoride ions. When the ion is larger, it's going to take up more space, causing the ions to move apart, causing the distance to be larger. And so magnesium fluoride has stronger attraction between its ions because the ions of magnesium and fluorine are closer together in magnesium fluoride, simply because fluoride is smaller than chloride. Now let's go ahead and try to apply these concepts to your proper intermolecular forces, which are for covalent compounds. And the first of these intermolecular forces that we really want to talk about are your dipole-dipole forces. What are dipole-dipole forces? Dipole-dipole forces is simply an attraction between two different polar molecules. And so if you look here, I've got hydrogen chloride and hydrogen chloride, and you have an attraction between two different neighboring hydrogen chloride molecules. And just to make sure we're all on the same page, what do these different symbols mean? This is a delta, a lowercase delta negative, and this is a lowercase delta positive. The lowercase delta negative means partially negative, partially meaning smaller than 1, and this is a partially positive charge, which means it's a less than positive 1 charge. And so the actual numbers for hydrogen chloride are positive 0.178 and negative 0.178. So you have a much smaller than positive 1 and negative 1. This is not an ionic compound. This is a polar molecule. And so you have partial charges on either side of this polar molecule. Now, you would imagine that the positive end of one of these polar molecules is going to attract the negative end of another polar molecule, which is exactly what happens. The positive and negative attract, and these two polar molecules attract each other. This happens all the time in all polar molecules. Now, before we go on, let's pause and think here for a second. This dipole-dipole force, do you think it's stronger than, the same as, or weaker than the ion-ion force? Pause here and think about it for a second. It turns out that the dipole-dipole force is much weaker than the ion-ion force, and that's because polar molecules have charges that are much smaller than positive or negative 1. Remember that the smaller the charge, the weaker the attraction. The larger the charge, the stronger the attraction. So in general, ion-ion forces are always going to be larger than dipole-dipole forces because dipole-dipole forces involve polar molecules that have charges that are much less than positive or negative 1. Let's compare a few compounds to see how this works. Li2O is an ionic compound, whereas H2O, as we all know, is a covalent compound, that is water. Lithium oxide has a boiling point of 2,600 degrees Celsius, whereas water has a boiling point of 100 degrees Celsius, much, much lower. And that's true in general. Ionic compounds typically have much higher boiling points than covalent compounds. And that just goes to show that the attraction between the ions within lithium oxide is much, much stronger than the attraction between neighboring water molecules within water. Well, pause there for a second and think about it. A lot of people think, well, aren't covalent bonds stronger than ionic bonds? Well, most of the time, yes, but remember that covalent bonds are not holding together water. They're simply holding together hydrogen and oxygen within a single water molecule rather than any kind of attraction between different water molecules. What's holding together water as a material are the intermolecular forces. That is the force of attraction between neighboring water molecules, and those are going to be your dipole-dipole forces. And you can see here that the dipole-dipole forces are much, much weaker than ion-ion forces. Now let's compare two different covalent compounds, H2O and H2S. Very similar in nature. However, H2O has a much higher boiling point than H2S, right? Water boils at 100 degrees Celsius, whereas H2S boils at negative 60 degrees Celsius. And so you can see here that H2S has a much weaker attractive force between neighboring molecules, right? Those intermolecular forces in H2S are much weaker than they are in water. Why is that? Look at the different dipoles. Water has a dipole of 1.85, whereas H2S, hydrogen sulfide, has a dipole of nearly half that, 0.97. That means that water is much more polar than hydrogen sulfide. And that happens because oxygen is more electronegative than sulfur. And you can see that the result is that those water molecules have a stronger dipole-dipole force of attraction between them than your hydrogen sulfide. In fact, the dipole-dipole forces in water are so strong that people have a special name for it, and that is hydrogen bonding. Hydrogen bonds are a special kind of intermolecular force. However, let's not get fooled by the name here. Hydrogen bonds are not real bonds. Okay, hydrogen bonds are, well, if they're not real bonds, what are they? They are extra strong dipole-dipole attractions. They're really just a form of dipole-dipole attraction, and they're a special form because they're only found in molecules with NH, OH, or FH. That is, molecules that can hydrogen bond must have a bond between nitrogen and hydrogen, or oxygen and hydrogen, or fluorine and hydrogen. So the molecule has to have a hydrogen in it, and it also has to have some other atom that is fairly electronegative. Nitrogen, oxygen, and fluorine are quite electronegative. And so when that happens, you can have a fairly strong dipole-dipole attraction. These hydrogen bonds are quite special because hydrogen is so small. And when hydrogen is so small, it's able to get closer to a neighboring partially negative oxygen, nitrogen, or fluorine atom, enabling a stronger dipole-dipole attraction because they are closer together because the hydrogen is so small. This here is a picture of hydrogen bonding in water, and you can see that oxygen is more electronegative than hydrogen. It has a partial negative charge, and the hydrogens, which are less electronegative, have a partial positive charge. And so you have an attraction between the partial negative of one oxygen and the partial positive of a neighboring water molecule's hydrogen atom. Now, because that hydrogen is so small, this oxygen is able to get fairly close to this hydrogen. But the bond length here was not a proper bond. The length of this hydrogen bond here is significantly larger than a covalent bond between oxygen and hydrogen. So keep in mind that this right here is an intramolecular force. It's a covalent bond between oxygen and hydrogen and is much stronger and much shorter than a hydrogen bond. The hydrogen bond itself is simply an intermolecular force. It's fairly strong in terms of intermolecular forces, but it's much, much weaker than a covalent bond, and it's much longer than a covalent bond too. But the hydrogen bond itself is fairly short as far as intermolecular forces goes, and that's why it's a fairly strong dipole-dipole attraction. The strong hydrogen bonding in water is one of the things that makes water have so many interesting properties as compared to other small molecules, and it's also very interesting that hydrogen bonding plays a role in life itself. Hydrogen bonding is key to the information that's stored in DNA and how it's transferred to RNA. And so why does A pair up with T and G with C? The reason is hydrogen bonding. The hydrogen bonds between neighboring base pairs in DNA are what enables them to know what pairs with what, and that's the whole basis for information stored in our DNA. Now, so far we've only been talking about polar molecules that are attracted to each other, but what about nonpolar molecules? Can nonpolar molecules attract each other at all? Well, you might at first think the answer is no. There's no kind of positive and negative in a nonpolar molecule, so why would they be able to attract at all? But it turns out that they can also attract each other through something known as London dispersion forces. Well, how does that work? First of all, one of our nonpolar molecules can get what's known as an instantaneous dipole. And this happens because electrons are always in motion. And so if electrons are always in motion, at any one instant, a nonpolar molecule can have a temporary dipole, which we call an instantaneous dipole. It's short-lived, it's not very strong, but any kind of molecule can experience this instantaneous dipole. This instantaneous dipole is going to be able to affect all of the molecules around it. And what it can do is it can induce or cause a dipole to form in a nearby molecule. For example, this chlorine molecule up here, which was normally nonpolar, has an instantaneous temporary dipole created within it simply because one or more of the electrons happens to be more on one side of the molecule than on the other, causing a partial positive on one side of the molecule. That partial positive on this side of the molecule affects its neighbor over here, causing the electrons from this molecule to want to approach the right side of that molecule a little bit more, creating a partial negative on this side of this molecule. And so you now have a partial negative here, which is attracted to a partial positive in this molecule. And so that instantaneous dipole and the induced dipole will attract each other, and those molecules will attract each other for a short period of time. We can look inside atoms to see kind of what's going on for a very, very simple example such as helium. Now, helium has very, very weak London forces, but let's see how it would work in helium. So here we have atom A and atom B. They can attract each other even though they're completely nonpolar. Well, why is that? because right here, atom B, those electrons just happen to be on the left side of that atom temporarily. And when they're on the left side of the atom temporarily, they're going to influence the electrons from atom A, causing these electrons to move over to the left some, as you can see over here. And so this here, atom B, would be your instantaneous dipole. And this atom right here would be your induced dipole, and you have an attraction between these two. Specifically, you have an attraction between the electrons from this atom and the nucleus of this atom. Now, this is probably a bit exaggerated in this example, but this is the way this works. You always have an attraction between the electrons of one atom or one molecule attracted to the nucleus of the other atom or other molecule. This attraction between the instantaneous dipole and the induced dipole is called London dispersion forces. This force exists between any type of molecule or any type of atom over the entire surface of the molecules. And so, although this is a very, very weak force, if you have very, very large molecules, it can actually be quite significant in terms of its attraction. The larger the molecules in the material, the more London forces, and therefore the greater attraction between molecules within that material. And so when you get to things like polymers, which are very, very, very large molecules, you can have a very strong London force between neighboring molecules because they're just so big. Now, let's go ahead and see how this is going to work in a few examples in our next slide. Here we have 3 different hydrocarbons, and because these are all hydrocarbons, that is molecules that contain only carbon and hydrogen, they're all essentially nonpolar, right? And so they don't have any dipole-dipole attraction within them. Now, what's the difference? First of all, this one is smaller. There's only 3 carbons, and this one are both larger. This has 4 carbons, and this also has 4 carbons. And so if we compare their boiling points, this molecule with 3 carbons and this molecule with 4 carbons, essentially you've just added a carbon and 2 hydrogens to this molecule right here. And when you did that, you notice that the boiling point has increased significantly. Well, why is that? It's increased significantly mostly because there's a greater number of London dispersion attraction forces between neighboring molecules simply because the molecules are larger, and that's going to cause a greater attraction between them, making them more difficult to boil, more difficult to separate. Now, what's going on here? This is C4H10 and this is C4H10, so they are essentially identical in terms of their molar masses, but they clearly have different boiling points. This one has a higher boiling point than this one. And why is that? The reason is that this molecule here is more elongated and therefore has a greater surface area and is able to touch its neighbors more frequently than this one over here. This one has a smaller amount of surface area per molecule, making those London dispersion forces smaller per molecule than you have in this one. Now, if you're wondering how these different intermolecular forces compare with each other, I made the following table. But keep in mind, this is not always accurate. Sometimes things are not going to follow these rules, but this is more of a general trend rather than a hard and fast rule. All right. In general, covalent bonds are going to be stronger than ionic bonds, and ionic bonds are going to be much stronger than hydrogen bonds, which aren't true bonds anyway. And hydrogen bonds are especially strong dipole-dipole forces, and London dispersion forces are going to be the weakest of all. However, as we already noted, if your molecules are very, very large, those London dispersion forces, while small in themselves, are very significant because you have so many of these London dispersion attraction between neighboring molecules, so that those London forces can be quite significant when you have very large molecules. Last of all, let's go ahead and try this out. What different intermolecular forces do the following compounds have? So here we have CH2Cl2. And CO2 and NH3, that is ammonia. Go ahead and pause this video and see if you can figure out which different intermolecular forces each of these has. Now, the first molecule, dichloromethane, or CH2Cl2, is a polar molecule, and so therefore, as a polar molecule, we know that it must have dipole-dipole forces. In addition to that, all molecules have London dispersion forces, and so it must have London dispersion forces. However, CH2Cl2, although it does contain hydrogen, cannot hydrogen bond. And the reason is it does not have NH, OH, or FH. It has chlorine, hydrogen, and carbon. It does not contain nitrogen, oxygen, or fluorine. Next up, carbon dioxide, as we know, is a non-polar molecule. Although carbon and oxygen have a significant difference in their electronegativities, because of the symmetry of the molecule, it's a non-polar molecule. And so therefore, as a non-polar molecule, by definition, cannot have dipole-dipole forces, and it also cannot have hydrogen bonds, in addition to the fact that it does not have hydrogen, and so it has only London dispersion forces. Last of all, ammonia, NH3. Well, everything has London dispersion forces. NH3 is a trigonal pyramidal shape, so we know that it is a polar molecule and therefore it has dipole-dipole forces. And it also does have hydrogen bonding because of that NH bond. All right. In fact, if any molecule has an NH, OH, or FH, you automatically know that it also has dipole-dipole forces simply because hydrogen bonding is really a type of dipole-dipole force. In fact, any molecule that has NH, OH, or FH must be a polar molecule because of the nature of your NH, OH, or FH bonds. That nitrogen, oxygen, or fluorine is definitely going to have a lone pair, causing it to be a polar molecule. All right, thanks for watching. Stay curious, and see you guys here next time.